Good day, ladies and gentlemen. My name is Dise Nyokong. For short, it's Dise. I'm the process manager for samplers, spirals, and magnetic separators at Multotec. Today, I'll be sharing something interesting, some of the things that Multotec has been busy with, particularly in the field of precision sampling. Today, I'll be discussing with you, particularly on what we refer to as the RAMA, and I'll unfold it as the time goes on with the presentation. And the highlight is what you need to know when you need to know it, because it's related to sampling. The outline of the presentation, the first three topics is something that you might be familiar with, starting with what is normally monitored in a copper operation, followed by what is conventional in terms of real-time measurement practices that we find in industry, not specifically related to copper, but for most commodities. And then I'll also go to just touch a bit based on process control versus metal accounting. And then I'll also then introduce you into this phenomenal RAMA system that we've come about to package this new system for most of our clients. And then it will just be lastly the recap. Now, what is normally monitored in a copper operation, what we know is, particularly in sampling, is normally the feed to the processing plant would have dry sampling equipment, and then that would be the feed that goes onto a conveyor, and then that's what we will normally put in a cross stream or a cross belt type of a dry sampler. And then when you are dealing with a copper sulfide, particularly on the flotation circuits on your slurry application, you will want to know what comes in and what goes out. Same as also more or less similarly on your concentrate stream. What you'll normally find is your dry sampling equipment after your filter press. And then on your copper oxide, similar to the flotation circuit, on your leach circuit, you would have or on your feed and also on your tails along your leach circuit, you will also put slurry samplers, and also on your tails applications also it's slurry, and that will what you normally monitor. And depending mostly on your feed and your outlet streams, that's where you normally put in your metal accounting samplers, and normally within your circuit, normally around your flotation circuit, sometimes you would have your process control samplers, but I will deal with that a bit later to explain the difference between the two. So normally, conventionally, in real-time analysis, you'll normally have an analyzer that is normally fed by a sampling device, depending on whether the application is under gravity or under pressure. But normally under pressure situation is what we refer to as a pressure pipe sampler that extracts a continuous sample that gets fed to an online analyzer and continuously produce an analysis of what is fed. But normally under these, you normally have a pipe and you normally have a probe inside your pressure pipe sampler that extracts a continuous sample to the analyzer. Second one, under gravity, it's what is referred to as a shark fin, and others, they will refer to it as a gravity assembly sampler. That also feed an online analyzer, but this one specifically, it's for gravity applications. Then under still under wet applications, because this is particularly specifically real-time, is normally mostly for slurry application. Yes, you do find others for dry application, but this one we will focus mostly on slurry application. For process control, we know that the samplers that are used to extract a sample from a process stream do not comply to theory of sampling. And what we mean by that is they extract a sample not across the whole stream, but a part of the stream all the time. That's why it continuously produces a continuous sample that goes to the analyzer. That's why the second point refers to continuous or time sample. So the process control as well doesn't always have to be a continuous sample that gets fed to an analyzer. It can sometimes be a sample extracted on a timely basis, and that gets analyzed into the lab, similar to what we'll normally see in a metallurgical accounting setup. But this would be using a process control sampler that does not comply to theory of sampling, and that normally happens under gravity and pressure, as I've shown in the previous slide. Now, when it comes to metallurgical accounting, the devices, or we can call it the samplers that are used, conform to theory of sampling. The main difference is that the samplers extract a sample right across the cross-sectional cut of the pipe, which is opposed to when process control samplers are used, that they take a sample apart inside a pipe, for example. And normally for metallurgical accounting, it produces timed composite samples, as opposed to most of the time for process control, where you normally have sometimes a sample being extracted continuously. And normally for metallurgical accounting, to comply with also theory of sampling, that is normally under gravity. So metallurgical accounting only complies for applications where streams are under gravity. Generally, as a not a rule of thumb, but as proven, to extract a sample representatively under metallurgical accounting setup, it needs to be in a gravity setup with 2 meters per second and less. Right? Here's just an indication of process control samplers as compared to the metallurgical accounting. The picture on the left-hand side represents a pressure pipe sampler installed in a processing plant, whereas the picture next to it is a shark fin type of a gravity assembly type of a sampler installed in a gravity application for process control. And then on the right-hand side here, it represents 2 pictures that shows a London crosscut sampler towards that's on the left-hand side in the metallurgical accounting setup picture, and the one on the right-hand side is a Vesen type metallurgical accounting sampler that can also be used. And if you can notice as well, both samplers are under gravity. Now, because I've explained the two setup of process control versus metallurgical accounting, now what Multotec proposes is using metallurgical accounting samplers to actually feed online analyzers, as compared to the conventional setup where process control samplers would be used. So that's why this name called real-time automated metallurgical accounting, referred to as RAMA, which is the new feed prep preparation system being proposed. What it does is it combines 3 disciplines, mainly metallurgical accounting instead of process control samplers. And then there's also an element of it where there's also preparation in such a way that there's no additional errors introduced into the system, such that the sample that is fed to the analyzer is as representative as possible. And then there's also the analysis part, which is the analyzer part. The first 2 are the ones that the RAMA system mainly represents. By that, then you will ask, how is the RAMA different from the conventional setup, and how is it unlocking value that is already there? Firstly, it feeds fully representative samples as compared to process control, as I've alluded previously. And by that, what it does is it removes about 80% of total sampling errors, which is normally associated with the process control type samplers. And by doing that, it brings a lot of value, whereby they can be improved grade control, they can be improved recovery, they can be also improved optimization of reagent consumption, for example, in flotation circuits. And there's also no need for analyzer calibration that is normally required with a separate set of exercise that needs to be done in process control samplers, whereas here you already have correct samplers used to feed analyzers. And then how does this setup really work? Is you will have an analyzer, and then right in a main process stream, you would have a metallurgical accounting primary sampler as compared to a process control pressure pipe sampler or a shark fin that is being used, and that will feed a hopper where timed increments that are collected into a hopper. Then from the hopper, these are fed into a secondary resin sampler, and that secondary resin sampler will produce a composite sample that can be used for metallurgical accounting, and the rejects from the secondary sampler will feed what we refer to as a salar pump that will then transport the rejects material to the analyzer, and then from the analyzer there will be a recycle back to the pump. And this setup is mainly used to ensure that, and I'll explain the features a little bit later into the presentation, but what happens is you've got a recirculation effect between the pump and the analyzer, thus to improve precision levels. Now that's how it works. And the sample from the salar pump, when it's done with the analysis, it's sent back to the main process. And what normally happens is, what's the main features of this system is from the hopper, the secondary resin, and the pump, that's where we refer to as the heart of the RAMA system. That's where we try to feed representative samples, and we packaged it very nicely so that it reports to the analyzer. This is just an example of how the hopper, the resin, and the salar pump is packaged inside a container such that it's easier to be packaged and be set up with the online analyzer. This is just an indication of the front view of the container onto which the RAMA system equipment is packaged. This is just the back side, and also showing how the RAMA system will actually be packaged inside a container. Now that I've shown, this might be discrete information shown to show it in perspective how this new system would look like as compared to the conventional setup. You will still have the analyzer, then you will have the main sampler in the main process stream. From there, that will feed the online RAMA system, which is packaged into the container. And then from the container itself, you will have a line that goes to the analyzer to be analyzed, and then you'll have that recirculating sample stream that I showed in the previous slide. And then from there, the material or the sample from the container will be sent back to the main process stream. So what other benefits that this setup brings into the whole sampling system is that the container itself is fitted with tilt, impact, and G-force gauges before departure. This is to help during handling, loading, and offloading, and to prevent damage to the equipment that is being installed inside the container. The container itself as well is also earthed, including the pipe rack inside the container. This is to prevent any lightning and injuries. Also, there's a crawl beam installed inside the container. This is to help and prevent any use of external crawl beams to be used in lifting the equipment. The control panel itself as well is also fitted with vibration dampers to prevent any vibration being sent to the control panel itself. Each flow line is also designed to prevent water hammers. By that, it prevents any damages and also increases or reduces downtime on the whole system. There's also a pressure regulator between the RAMA system itself and online analyzer to prevent any premature failures of the line and also any damages to the online analyzer. Further, there is also a dedicated line that is sent to the analyzer. This is to prevent any cross-contamination that normally happens with conventional analyzer setup between the process control samplers and an analyzer. There is also that with each stream, as I showed earlier, that there is a recirculating line that ensures that the stream is recirculated 3 times at least to the analyzer, thus to improve precision levels as compared to conventional, where it's normally one stream that is sent and there's no recirculation. There's also automated wash water cycle per analysis to prevent also cross-contamination. There is also air agitation points installed on all pipelines. This is also to prevent any blockages. There's also abundant rod within the container itself, so that if there's any spillages, it acts as a force flow. And just to recap, previously I mentioned in the previous slide that there are various streams that have been analyzed in a copper beneficiation process. And normally what is used is process control samples that are being fed to analyzers that are biased. And thus, Multotec has proposed a RAMA system that eliminates 80% of errors, whereby key stream parameters are accurately presented, therefore improving on ensuring that there's better grade control and there's recovery optimized on reagents. And with that, thank you for listening, and hope that has unlocked and struck you with a new way of analyzing for samples in a beneficiation process. Thank you.